Hey students, in this video we're going to cover antiderivatives and initial value problems. There's a lot of content here. I'll try to keep it pretty quick. So our main idea here is the antiderivative of a function is not a unique function. There are several functions that have a particular derivative, but for each function, its derivative is unique. So when we're doing antiderivatives, we want to ask ourselves, what general function has this derivative? And so for example, one, we're going to derive the general power rule for integrals. So if we have like f of x equals x cubed plus 2x squared plus 7x plus 1, let's go through the steps of finding its derivative. Oh, let me, did I open this in notes? I think I did. I'm pretty sure I did. So let's hop over to the notes app. This is for Cal 3. Yeah. All right, so we're actually here. So, all right, so we know our derivative is f prime of x equals. Now, what the general power rule tells us for derivatives is we multiply the 3 to the front. We have x, and then we have 3 minus 1 as our exponent. Then we have 2 times x to the 2 minus 1 power. Then we have plus set. Let's rewrite this, and we have plus 1 times 7 times x to the 1 minus 1 power, and the derivative of a constant is 0. So now, of course, we know this is actually just 3x squared plus 4x to the first plus 7x to the 0. So imagine that we reverse the steps of differentiation. So when we derive, we multiply the exponent to the front, and then we subtract. When we're doing antiderivatives of polynomials, the first thing that we want to do is add to the exponent because we subtracted from the exponent. And the inverse operation of multiplying by the exponent is going to be dividing by that new exponent. So when we're going backwards, the first thing that we're going to do is, let's talk about some new notation. So if we want to find the antiderivative for this function, we need a symbol for that. So this symbol means antiderivative. So this funny looking S that you've probably seen is going to be 3. So it's the antiderivative of 3x squared plus 4x plus 7. And we'll talk about this dx in a moment, but it's just like tiny changes in x. So what this means is reverse the process of differentiation. So what we're going to get is, so we're going to keep that 3x squared, but now we're going to have 3x to the 2 plus 1 power, and we want to divide by 2 plus 1. And then we're going to have plus 4x to the 1 plus 1 power divided by 1 plus 1, and plus, all right, so that's, the 7 is technically 7x to the 0 power. So we're going to have plus 7x to the 0 plus 1 power divided by 0 plus 1. But remember, we lost the 1 here because the derivative of any constant is 0. So we're just going to add some arbitrary constant at the end. So when we simplify this, we're going to get, what, 3x cubed divided by 3 plus 4x squared divided by 2 plus 7x to the first divided by 1 plus that indefinite constant. So simplify where you can. We get x cubed plus 2x squared plus 7x plus any constant. And so specific to our problem, that constant is 1. What that would tell us is that really f of 0 equals 1. And so this is an initial value condition where if we know some value of x, it gives us a unique function instead of this general antiderivative. But we'll talk more about that later in the video. So as I said, we have like this new notation. We have this integral symbol. It represents the antiderivative of a function. And what we learned in linearization is that small changes in y can be predicted by the derivative of some function times the small changes in x. So if we're like working backwards from that, then we can get the y from this general change. And so that's just where this integral symbol in the dx comes from. Now, specific to polynomials, we have this general power rule where we have the antiderivative of x to some power is x to that power plus 1 divided by that power plus 1 plus some constant. I should mention that if n is not equal to -1, because then if n is -1, we have -1 plus 1 is 0, and we can't actually divide by 0. So for our second example, we just want to apply the general power rule where we can. Add 1 to the exponent, divide by that new exponent. So this is going to equal x to the 3 plus 1 divided by 3 plus 1 plus x to the 2 plus 1 divided by 2 plus 1 plus x to the 1 plus 1 divided by 1 plus 1 plus some arbitrary constant. So that's going to be x to the 4th over 4 plus x cubed over 3 plus x squared over 2 plus c. So again, all we're doing is reversing the process of differentiation. From this function, if we found its derivative, we would get, we should get what we started with. So let's add in one thing. We're going to make this general. So the antiderivative of a derivative is going to equal that function plus a constant. So here, think about this being a derivative. What we end up with is some function f of x, again, plus some constant. So moving to our next example. So when we're doing antiderivatives or derivatives, really, constants don't affect how we find a derivative. They affect the value of the derivative. They don't affect the process, how we do it. So if we have like a constant multiplied by some function, you just apply the same rules for antiderivatives and then adjust for whatever calculations the constant presents. So for example 3, we're going to find the antiderivative just like we generally do. I'm also adding in the antiderivative of a constant is that constant times whatever variable, because the derivative represents slope. So for a constant, it just means that it was the slope of whatever line that produced it. So for example 3, the antiderivative of 3x squared is 3x to the 2 plus 1 divided by 2 plus 1 plus 2x to the 3 plus 1 divided by 3 plus 1 plus x to the 1 plus 1 divided by 1 plus 1 and minus 5 times x to the 0 plus 1 divided by 0 plus 1 plus whatever constant. So now once you get the hang of this, you don't have to do this whole plus 1 plus 1 plus 1 divided by whatever plus 1. You can go for the shortcuts. So this is going to be 3x cubed divided by 3, which is just x cubed. This is going to be 2x to the 4th divided by 4. So 2 over 4 is x to the 4th divided by 2 plus x squared divided by 2 minus 5x to the first power plus c. So we're going to say f of x equals, and again, we're basing this on assuming this is our derivative. For example 4, so the general power rule only works when we have x's not in the denominator. When that happens, we have to like rewrite our function so that the x's are not in the denominator. And if we have rational radicals, we have to turn them into rational exponents. So our rewrite step is going to be the antiderivative of x to the -1 minus 3x to the negative 2 minus, so this is x to the 1/2 in the denominator, so minus x to the negative 1/2 dx. Do not confuse the rewrite step with actually finding the antiderivative. So now we want to apply the, actually I meant to make this x cubed because we said the general power rule doesn't work for 1 over x. Make that 1 over x cubed. We're going to make this x to the negative 3 instead. My apologies. So make that x to the negative 3. So what we're going to get is x to the negative 3 plus 1 divided by negative 3 plus 1 minus 3x to the negative 2 plus 1 divided by negative 2 plus 1 minus x to the negative 1/2 plus 1 divided by negative 1/2 plus 1 plus some constant. So that's going to be x to the negative 2 divided by negative 2 minus 3x to the negative 1 divided by negative 1 minus, so now for integration, anytime that you're adding 1 to the exponent, you can really just add the numerator and denominator. That's your new numerator, and the denominator stays the same. So like negative 1 plus 2, that's 1. So we're going to get x to the positive 1/2 divided by 1/2 plus c. So if we fully simplify, that's going to be negative 1 over 2x squared plus 3 divided by x to the first minus dividing by half is the same as multiplying by 2, so minus 2x to the 1/2 plus c. So again, we'll say f of x equals that under the assumption that this was a derivative. Cool. For example 5, there is no product rule for antiderivatives. We can't do the antiderivative of one thing times the antiderivative of another. When possible, we have to like simplify before we can find the antiderivative. So first we want to just multiply everything out. So we're going to get the antiderivative of 6x squared. So then plus 4x minus 3x is going to be plus x, and then minus 2 dx. So now this is in the form where we can find antiderivatives. So this is going to be 6x to the third. Let's take some shortcuts. So it's going to be 6x to the third divided by 3 plus x squared over 2 minus 2x plus c. And then when we simplify, we're going to get 2x cubed plus x squared over 2 minus 2x plus c. I said there is no product or quotient rule. So if we have a quotient, if possible, simplify the quotient. So here, make this x to the 5th power in our denominator. Make that a 5. So x cubed so we know how when we divide the same base, you can subtract the exponents. So 3 minus 5 is negative 2. So this is going to give us x to the negative 2 minus x to the negative 3 plus x to the 0 divided by x to the 5th is x to the negative 5 power. We're going to add on a differential. So now when we add, we're going to get x to the negative 1 divided by negative 1 minus x to the negative 2 divided by negative 2 plus x to the negative 4 divided by negative 4 plus c. And again, fully simplified, that's going to be negative 1 divided by x to the first. We did not switch places with the negative 1 and the x. 1 divided by negative 1 is negative 1. And so then we're going to get plus 1 over 2x squared because this negative divides in that negative and makes a positive. The 2 stays in the denominator. So then we're going to get minus 1 over 4x to the That should be 4. That should be 4x to the fourth. 1. So 1 over 4x to the fourth and plus c. So for the exponential function, we'll see if we can come up with a rule for its derivative, antiderivative. So if f of x is equal to this, f prime of x using the chain rule is k times e to the kx power. So to get the derivative of the exponential function, we multiply by the derivative of the exponent. To get the antiderivative, we want to divide by the derivative of the exponent. What that's going to mean is that if I have the antiderivative of e to the kx dx, that's going to equal e to the kx power divided by k plus c. So specific to let's create an example. So say we had the antiderivative of, we'll say, e to the 3x plus e to the negative x minus e to the 1/2 x plus 4e to the 2x dx. So now using that rule, we're going to get this is equal to e to the 3x divided by 3 plus e to the negative x. The derivative of negative x is negative 1 minus e to the 1/2 x. The derivative of 1/2 x is 1/2 plus 4e to the 2x divided by the derivative of 2x is 2 plus a constant. So if we fully simplify, it's going to give us e to the 3x divided by 3 minus e to the negative x. Dividing by half is the same as multiplying by 2, so minus 2e to the 1/2 x plus 2e to the 2x plus c. So that's for the exponential function. When we encounter dx over x, 1 over x, or k dx over x, that's going to be the antiderivative of, the antiderivative is going to be the natural logarithm. So what that means, so let's look at this. The antiderivative of 1 over x dx, that is x to the negative, the antiderivative of x to the negative 1 dx. So remember we said the general power rule works for everything that's not n equals negative 1. The case of negative 1 comes up, its antiderivative is the natural logarithm of x. So remember that if we have f of x equals the natural logarithm of x, the derivative of the natural logarithm of x is the derivative of x, which is 1, divided by x. So if we're asking whose derivative is 1 over x, that's the natural logarithm of x. So quick example, if we had the antiderivative of, we'll say 1 over x minus 3 over x minus 1 over 4x dx, that's going to equal the natural logarithm of x minus 3 natural logarithm of x minus 1/4 natural logarithm of x plus c. And so the trig function, the last thing is the trig functions that we have, or the rules are going to be as follows. So if we have the antiderivative of cosine x dx, so whose derivative, we'll actually make this more general. So if we have the antiderivative of the cosine of some multiple of x dx, so first off, whose derivative is cosine? Well, that's going to be sine, we'll make that sine kx. That's going to be the sine of kx, but then we have to divide by k, because if you take the derivative of sine kx over k, you're going to get cosine kx, plus c. The antiderivative of sine kx dx is whose derivative is sine? Well, the derivative of cosine is negative sine. So the derivative of negative cosine is going to be positive sine. So this is going to be negative cosine kx over k plus c. And then the antiderivative, what other ones do we know quickly? Secant squared kx dx. Whose derivative is secant squared? That's going to be tangent. So it's going to be tangent kx over k plus c. And we have the other ones, but we'll talk about those in class. So a quick example, and then we'll conclude. So say we had the antiderivative of the cosine of 3x minus the sine of, we'll say, 1/2 x plus 5 secant squared 6x dx. This is going to equal, so the antiderivative of cosine is sine. So we're going to have sine 3x divided by 3. The antiderivative of negative sine is positive cosine of 1/2 x divided by 1/2 plus 5. The antiderivative of secant squared is tangent. So tangent 6x divided by 6 plus c. Simplify where you can. So that's going to be sine 3x over 3 plus 2 cosine 1/2 x plus 5 over 6 tangent 6x plus c. And that is our final answer. All right, so kids, that's the video on antiderivatives. In class, we'll talk about initial value problems and hopefully move on to Riemann sums. There's a lot of information here, so if you have to go back and rewatch, please do. Also, please ask questions in class. Thanks for watching.